So I will talk about some parts of my PhD with Véronique Lazarus and Raoul de Moirapino from the ENSTA and Safran Aircraft Engines, respectively. Thank you very much. So I'm going to talk about the iterative perturbation method. So as a motivation for this stuff, I will briefly talk about basic damage tolerant design. So what we need to do is compute fatigue lifetimes of some cracks. And globally, you need two things to do that. You need first, well, at the end, a propagation law, but you also need to be able to compute stress intensity factors for the crack shapes that you want to be able to handle. And so right now, this is this part that we will focus on. So we will only talk about computing stress intensity factors for weirdly shaped cracks. Actually, currently the methods that are used in the industry are fall into two categories. On one side, you have semi-analytical tools. So these tools rely on simplification of the crack shape geometry and actually simplification of the geometry of the problem overall to be able to very quickly and very efficiently compute stress intensity factors values at some privileged points of the cracks. So this is a first downside. You don't know the stress intensity factor everywhere on your crack. So when you propagate this crack, you have to do with limited information. So since it assumes very strict simplifications, it can be extremely conservative. And in general, the result you can get from these methods can be quite off from the real lifetime of your parts. And well, you can see the list of downsides goes off the slide. And so if this isn't good enough for you, you have to use very costly methods from a computational point of view, which not only 3D finite element methods, but you can also have XFEM or stuff like that. But globally, these methods are going to be very precise. They are going to give you a lot more of information, but you have to pay the cost of waiting for a few days or weeks for your results, which, well, it's not convenient to say the least. So between these two different approaches, there is not of existing alternatives, at least in the industry. And so one alternative that I would like to introduce to you is the perturbative method. So say, for example, you have some case which looks simple. You already don't want to use 3D finite element methods for that because it looks simple. So say you have a planar crack, you have only mode 1, it's fairly simple, so you have something like that. But at the same time, you see that the shape of the crack is really quite not that simple. So it's not going to be possible to handle with semi-analytical methods. And so at the end, you have a dilemma. Or you choose to make very drastic approximations and use semi-analytical methods and have a result now, or you are going to do 3D finite element methods and wait a long time. So a good middle ground would be the perturbative method, and that is what I will talk about. So the problem we are going to tackle is the case of an internal crack, planar crack. So the fact that it is planar and inside a very large body is the only hypothesis we will make on the geometry of the problem. And we also make the not absolutely necessary, but for the sake of simplicity, supplementary assumptions that there is only mode 1 and everything is uniform and isotropic. So we are going to focus on the stress intensity factor because it is the quantity we want to look at. And we are also going to follow the W function, so-called fundamental kernel, which can be understood as a measure of the influence of a loading near some point of the crack on the stress intensity factors value at another location of the crack. And so, yeah, I already talked about that. And so the idea of the stress intensity factors is that, well, given some small perturbation of the crack, small advance delta A along the crack front, you can compute the variation of stress intensity factor and W along the whole crack. So it's only an integral along the contour of the front. So, and in this integral, there is only W stress intensity factor and the advance. Looks simple enough, right? So not that simple, because actually these formulas are only good for perturbations that are zero at the point where you compute your variations. And we want to handle arbitrary variations. Without that, it's not really useful to compute variations if they need to be zero where you do the computation, and you want to do the computation everywhere. So trivial perturbations are not really interesting. So what we do is that we use auxiliary perturbations to help us. So we can add another perturbation on top of our initial perturbation to ensure that our crack advance is zero where we want to. And we can choose this auxiliary perturbation to cause an auxiliary variation of K and W that is easy to compute. So we would like to choose this auxiliary perturbation delta star A and delta star A to make these terms as simple as possible. And ideally, they would be null. Is this possible? We will see. So globally, how to choose these two auxiliary perturbations? We will choose perturbations that doesn't change the shape of our problem. So this will be perturbations that correspond to affine transformations of the crack plane. And so globally, these are going to be combinations of translation, scaling, and rotations of the crack plane. And well, for W, all these transformations are going to have absolutely no effect on W, because it's W only depends on the geometry of our problem. So it will be easy. And for K, if our media is uniform and isotropic and all that, it's going to be easy as well. And so, for example, that's what you get for delta S star. You want to go from the SIG black line to the SIN black line. And so at some point S0, if you want to do that, you need to have non-null perturbation. So first, you translate your crack, that's the red line. And so the resulting perturbation between the red and the SIN black is zero where you want it to be zero. But now you should be a little bit suspicious. Does this transformation really incurs no change in the stress intensity factors? Well, no, in general. So it's only zero if you have uniform stress or remote loading. So from the point of view of the crack, all the loading is uniform. But it's not really funny if the loading is uniform, right? We want to be able to handle local residual deformations that cause residual stresses or stuff like that. And so in this case, yeah, we're going to see, so there is a little bit of math, but it's here to show you that the only math you need to see to understand how it works. So it's really easy. I want really to convince you that the method is quite easy. Given the crack face weight function of our crack, we don't know what it is, but we know that it exists. If we translate the crack, it's the same thing if we translate the stress, right? And so we can just make a gradient of the stress in the crack plane appear. And so we can see delta K star as the stress intensity factor of some auxiliary front, which is a front of the same shape as our original front, but subject to loading, which is the differential of our initial loading. And since computing delta K is easier than computing delta W, it is almost free from a computational point of view. So you can have a series of fronts that are subject to different stresses and that are used to compute the variations of stress intensity factors for all your hierarchy of crack fronts. And having all these ancillary fronts is not really a problem because the W for all these fronts are going to be the same since their shape is the same. And and you use the stress intensity factor values to update K and W as the crack advances. So is it all? No, not quite. We need to be able to start because we only compute variations of K and W. So the only reliable starting point we know is choosing a circular crack. And so we need two steps in our simulation. First, we need to be able to choose a circular crack and modify it so it fits whatever shape we want at the start. And once we have this very shape, but now with non-values of K and W, we can choose whichever propagation law we want and let the crack propagate in a physically sensible way. And so it's worked pretty well. So it's not as instantaneous as a semi-analytical method. So you see for a quite good error on the stress intensity factors, you have to wait a few seconds. It's not just the click of a button. You have to, you can take a breath. But I am hoping we can convince the folks in the design offices that it's still okay. And so, like, the method can be applied quite successfully. So in a paper from a few years ago, we used the method to simulate the fatigue growth of all these cracks. On a side note, yeah.
1 minute.
Sure. On a side note, for all these cracks, since at the end of the fatigue growth, everything is pretty circular, we can force the end crack to return to a circular shape and check that at the end of the simulation, the accumulated error is still on the same order of magnitude of what we had just at the present slide for just an elliptical crack. And so, yeah, it's working, but in the sense that we can perform complete simulation of fatigue growth with this method, and it's quite good from a computational point of view. But we are not quite there yet because we still want to handle more difficult cases. We want to handle surface cracks when you have an edge. And remember that a lot of what I showed worked because we were able to translate and change the configuration freely. But if you have an edge, it's not that easy. So there are ways to try to fiddle with the auxiliary perturbations and still have it work. But there is a trade-off, and we're working on that. Thank you very much.
Thank you. One question with a short answer, if any. Yet another relatively complicated stuff, to be not honest, but if no, thank you once. Oh yes, Jacques.
I guess this is only for purely elastic materials.
Yeah. We are working the framework of linear elastic fraction. Yeah, because no plasticity at all, because we only consider fatigue growth, and so relatively low loading of the.
Do you have any explanation for this weird shape?
Yeah, actually, I didn't have to talk about it, but it's surface crack with the surface which is cold rolled or shot pinned, or the result of an impact, which called very heavy compressive residual stresses, and it tends to trap the growth of the crack and causes these weird shapes. And these weird shapes are, as I'm sure you guess, not very well handled by the semi-analytical methods.